is not what actually melts. What melts is the actual overlying mantle. And that happens because you introduce water into the mantle by whatever means. And believe it or not, a wet rock melts at a lower temperature than a dry rock of the same chemistry. So if you were to heat a rock and add water to it, that would lower the melting point. So basically, the introduction of water into the mantle is what's generating these melts. And these melts, they're more buoyant than the surrounding rocks, and they migrate up to the surface and generate these chain of islands. So, yeah, as I said, the Lesser Antilles arc. The volcanoes from Sabre to Grenada. There are roughly 19 volcanoes which are thought to be live, for want of a better word. And basically, the idea is that these can erupt in the future. The eruption frequency in the Caribbean is not that high, and that's simply because the subduction is around 2 centimeters per year, which is fairly slow. If you compare that to other arcs such as Japan and Indonesia, I think they're going at like 7 centimeters and 9 centimeters per year, so it's a bit quicker. So because of this, you're able to generate eruptions quicker. There's also more earthquakes. So everything is happening quicker in these other arcs simply because the rate of subduction is faster. But all of the phenomena that we see occurring in these areas, we can get in the Caribbean. So we can get earthquakes, we can get tsunamis as well. So volcanic earthquakes are not uncommon in the Caribbean. Some countries, such as Dominica, they get numerous seismic swarms, which is what these volcanic events are referred to as. Another manifestation of volcanism would be these hot springs or soufrieres, if you like. And those are quite common down in the windwards as well as up in the leewards. So the fact that we see in these soufrieres, these sulfur deposits, steaming ground, that suggests that you've got a magma chamber at depth, which basically says there's a volcano there, even though it's not obvious, because some volcanic mountains are not really easy to see, and it depends on the scale you're looking at. But the idea is, whatever it is that's happening in Japan and Indonesia can happen here. And these volcanoes and islands are here because of the subduction that's happening off to the east. And if you look closely at in terms of the spacing of these islands and where they are relative to the trench front, it seems fairly straightforward that you get them around 150 to 2 kilometers from the trench and roughly the same distance above the point where melting occurs. So this slide here just gives you an idea of, or confirmation, if you like, from the earthquakes that there is actually subduction. Basically what this slide is showing is that you see a shallowing of events from east, from west to east, rather. So as the deeper the slab gets, the deeper the earthquakes are. And basically the earthquakes are generated by friction between the override and the downgoing slab, but also physical breakup of the downgoing slab. So this sort of earthquake evidence basically confirms that, yes, there's subduction going on and we've got arc volcanism happening in the region. So what is so unique about arc volcanism, you ask? Most of us are familiar with looking at eruptions in Hawaii, which is a basaltic province, or even in Iceland. But the lavas in these regimes are quite different. First of all, the viscosity is higher, and that's a function of the silica content. So the magmas are stiffer. They're slightly cooler, maybe 100 or 200 degrees cooler in some cases, probably a bit more. But that is irrelevant if you're dealing with temperatures in excess of 500 degrees Celsius, because the human body does not like high temperatures anyway. So if you're hit by a 500 degree pyroclastic flow or a lava flow that's 1,000 degrees, it makes no difference. That's still a detrimental situation to be in. But basically, because we've got higher viscosity lavas here, we get more explosive eruptions. Because the lavas are stiffer, they tend to trap gas more readily. So the idea is, based on the regime you're in, you're more likely to get explosive volcanism than in other regimes. And in our regime, luckily enough for us, these volcanoes are fairly explosive. And one of the artifacts of these high viscosity lavas is that they tend to build these steep-sided volcanoes, which you can identify easily in the region because the volcanic islands are quite easy to see versus the non-volcanic ones, such as Antigua. Okay, so eruption styles and hazards. Most people who have witnessed this eruption would have seen all of these events unfold at some point in time. And the most common event that we would see would be the building of lava domes. And this, all of the mountains that we see on island are actually old lava domes from previous eruptions from different centers. So as Dr. Stinton mentioned yesterday, Purchase Mountain, Chances Mountain, Galway's Mountain, these are previous lava domes from previous eruptions, which were left in place at the end of the said eruption. But lava domes generate pyroclastic flows when they collapse. And as I said, because of the high viscosity nature of these lavas, sometimes you generate explosions, which can also generate pyroclastic flows from column collapse. One of the other things that we get here, although on a much smaller scale than other volcanoes, are lateral blasts. And basically what that is a directed explosion. And that has a lot to do with what the volcano is doing. So a few examples which I'll come to later. Basically, if you undermine the dome in a particular area, what you would do is you would expose this gas-rich material, and that explosion would go through that gap in whatever direction it is. And there are a few examples of that happening here. Another common hazard that we face are lahars or mud flows, but those are not directly related to volcanism, at least not in Montserrat. They're related to the rainy season and the availability of material to be transported down the guts or valleys to generate these lahars or mud flows. And lahars or mud flows can be quite dangerous because what you have is a slurry of rock and ash and mud, and some of them can actually conceal large boulders in them. So there have been situations in the past where people have tried to cross the Bellum Valley with a lahar coming down, and I guess some of us know what happened. There have been vehicles lost, but luckily no loss of life. Okay, so pyroclastic flows. This is the most common hazard that we face here. And basically, as I said, there are two modes of generating pyroclastic flows. You can either disrupt a dome and generate an avalanche down the flanks of the volcano, or you can generate an explosion, and over time the material from that explosion will lose its buoyancy and fall back down onto the flanks of the volcano and generate pyroclastic flows more or less radially. Now, there are two main differences between these two types of flows. First of all, a dome collapse flow would probably have more material available for it to tap into. So there's always a possibility that it could have a longer runout distance, because runout distance has a lot to do with the volume of material and the energy of the actual event. These column collapse flows from explosions, they're limited by the volume of the actual explosion. But what they're not limited by is the topography, so to speak, because the material is falling back down onto the summit of the volcano. So the flows are not that constrained and can go more or less in any direction as in opposed to a dome collapse flow where proper monitoring of the dome would give you an idea of where the collapse would go and give you an idea of how large it would be. But pyroclastic flows are quite hot, they're fast-moving avalanches, and you definitely cannot outrun one of these things. So one of the problems that we have in Montserrat is we try and not be in the way of these flows. So there are times when we have to be preemptive in terms of our thought process. And if we think that the flow is going to be generated in a particular area, the best option is to not have people there, because if there are people there when it starts, then it's probably too late. Okay, so I just want to speak about the, because these are terms that will come up, but in terms of the seismic waveforms that we encounter in Montserrat, and they probably mean slightly different things. But if you look at this slide, you can see there's words like volcano tectonic event, hybrid events, long period events. And they're generated by different mechanisms, if you like, and they mean slightly different things. So for instance, if we're seeing a swarm, which is a large number of earthquakes over a short period of time, containing mostly VTs, then in our mindset that these events are associated with the fracturing of rocks by either gas, fluids, or magma, if you like. So if we see VT events, then we think, okay, there's magma moving. Hybrid events, sort of like VT events in terms of they have a sharp onset, but there's also a low frequency ending. And we consider those to be gas resonating in the conduit after fracturing events, whereas long period events, these low frequency events, those are more or less bad news. When you see in loads of long period events, it means that magma is flowing freely through the system. So you get sort of like a pipe organ effect or a standing wave like effect. So it depends on what sort of seismic activity we're seeing, then we will respond differently. Rock falls, as you know, they're basically pieces of the dome crumbling and like rolling away from the dome down valleys. If they're big enough, or if they're even bigger, they're referred to as pyroclastic flows, because that's just a volume thing in most cases. And then the LP rock falls, which is a rock fall generated by a long period event, and a long period event shaking the dome and causing pieces of it to fall off. So basically, when we look at the content of our seismic signals, we should be able to have a good idea of what's happening. Because if the dome growth is high, you would expect loads of rock falls. If the extrusion rate is high, you would expect an increase in LP activity and probably VTs as well, and probably hybrids. So it's all about knowing what each signal may or may not mean as we're looking at it. Okay, so as most people would be aware, this eruption was not out of the blue. There have been several instances in the past where there were seismic swarms, seismic crises, if you like. And they were basically spaced roughly 30 years apart. And these were documented properly by different people. The first set of, or the first seismic crisis, if you like, occurred in the late 1800s. And they were definitely felt events. Now, it's fair to say that given that we've got instrumentation on these islands now, we know that the number of felt events in any seismic crisis is a very small fraction of the number of events that actually happen. So, for instance, the seismic crisis we've been having over the past 20 years, if you look at the number of actual events that the instruments pick up versus the number of reported felt events, it's quite small. So, for instance, in the 1895-1902 crisis, there were felt events. In the 30s, there were also felt events. There were 3,000 felt events, apparently, in the 30s. Now, that says a lot, because it means that there was a significantly larger number of earthquakes which actually happened, but people did not feel them because they were too tiny. And that's one of the things about volcanic earthquakes. They tend to be smaller than tectonic events, so they're not normally felt. But our instrumentation that we use, the seismometers, they're quite sensitive, so they would pick these events up. So the most recent seismic crisis, which would have happened in the early 90s, eventually led to this eruption. But as we said, every 30 years, roughly every 30 years, it seemed like this volcano was trying to erupt. So the 1990 crisis, or the crisis in the 1990s, which led to this eruption, it should have been no surprise that these earthquakes occurred. It also, when you look at this graph, which I'm displaying, it also should have been no surprise by the end of 1994 that there was an eruption coming, because there was a sharp increase in the number of events leading up to the July 95 surface activity. So one of the things we look at in these crises is not just the number of events, but how much the numbers are increasing by. So a cumulative plot of the number of events would give you an idea of the rate at which they're occurring, and gives you an idea of how serious the situation may or may not be. So you can see quite clearly from late November, December 94, there was a huge jump in terms of the number of events. And, well, it's hindsight now, but knowing what we know now, we should have been able to, well, not we, but someone doing this job, and there was no one doing this job because we don't have volcano observatories all over the region. But whoever was looking at this data could have said, okay, there was definitely an eruption coming, because you can see that build up to 95. Okay, so eruptions. Why do these volcanoes erupt? We all know that these volcanoes can stay quiet for years and do nothing. I'm fairly certain that there are some people in Montserrat who do not even know that there was a volcano present, because I guess back then, associating the fumarolic fields with a volcano was not a straightforward thing. And if you don't know, you don't know. But the idea is, when we're looking at these subduction zone volcanoes, there are a number of things which are quite common to them. And if you look at this photo, you can see a darker lava, if you like, surrounded by a lighter lava. Now, the lighter lava, in our case, would be andesitic lava, which is like the majority of what's being erupted. But this darker lava, what it is actually a basaltic magma, which would have come into the chamber. It would have brought heat and gas with it. And eventually what it does is it remobilizes the actual magma that was sitting in the reservoir beforehand. So it brings heat and fluids, it mixes with the andesite that was sitting there and drives it to the surface. So the evidence that we see in these rocks, which is the enclaves, suggests that most of these eruptions in subduction zone volcanoes are carried out by magma mixing. So you mix a magma, it's hotter, it's gas rich, it's probably going to move your residing magma forward. There's also a space problem as well, because if you've got a reservoir of a fixed volume and you put more magma into it, then you probably would run out of space. So you'd have to start putting material onto the surface. So basically what we think is happening, or did happen, is that we've got this basalt, this hotter gas-rich magma, which came into the base of the andesite reservoir, remobilized it, and generated this eruption. And as I said, the proof is actually in these enclaves, which are quite common throughout the entire eruption. And as you can see, they vary. The volume of enclaves that we see varies over time, but they're always in these in the lavas that we sample. All right. I want you to pay attention to this plot. This is what we call a multi-plot And basically what was done is that we compared a number of different parameters that we measure from this volcano on the same plot. So as you can see, and most of us know that this eruption has not been continuous by any means. It's been stop, start, if you like. So what this volcano would have done was erupted for about 3 years, take a break for about 18 months, erupted for another 3 years, take another break, and it did so on and on. If you look closely at this graph, there are a number of things that's obvious. The top part of the graph shows the number of seismic events that occur over time. And as you can see, that is quite well correlated with the pink areas. And the pink areas are when there's actually extrusion at the surface. Now, it's fair to say that most of these seismic events are rockfalls, but there are quite a few earthquakes in there as well. So seismic activity correlates well with extrusion. As you can see, when it's not extruding, which is the green parts, there's virtually little or no seismic activity. Most of the seismic activity that occurs in these pauses are earthquakes. The second graph, which is a deformation graph, and we use GPS to look at the deformation. And what it does show is that there's a distance change between two GPS points over time. So during periods when it's not erupting, we see what's considered to be an inflation signal, whereas the reservoir is actually swelling. During times when it's actually erupting, the reservoir is contracting. And the mindset here is that we've got a continuous trickle of basalt into the reservoir. So when you're not pushing material out at the top, you're increasing the volume or the capacity of the reservoir. And then when you're not erupting, when you're erupting, the capacity goes down. When you're not erupting, it goes up. So as you can see, for every green portion, the line is going up. And that's been the case since 2010. So we've got continued deformation or continued influx of basalt, if you like, since 2010, if that's the interpretation that we use. Another thing that's obvious on this plot is the SO2 flux, which is the lower graph. And basically the SO2 flux has been more or less continuous throughout the eruption. So and another thing that's quite obvious is the duration of the eruptive episodes. The first 3 episodes were much longer than the most recent ones. I mean, what you don't get from this graph as well is the violence of the eruption, but I would speak a bit about that later on. But basically what did happen was that as the eruption went on, the violence of it increased. And from around 2007 until 2010, the number of explosions were much higher. Right, cool. Phase 1. Now, I'll spend a bit more time on phase 1 than the other phases. And the obvious reason is that almost everything that happened in phase 1 was new and notable, if you like. So, like most of the other episodes that we have here, phase 1, I mean, it's characterized by dome building, dome growth, collapses. There weren't a lot of explosions, but there were some. The extrusion rate was around 4.5 cubic meters per second. And the largest dome that was built during this episode was 113 million cubic meters, which is, well, by other standards, is fairly small. I think the significant thing, or one of the significant things about this extrusion phase was the Mother's Day event on May 12th, where you had flows hitting the sea for the first time. I think that was significant because most people wouldn't have seen that before. What they wouldn't have seen as well before is how the flows interacted with the sea, and you actually have flows which are capable of traveling over the water at some distance. Another unique thing that happened in phase 1 was the explosion of September 17th, 96. And that happened after 9 hours of dome collapse. You know, so I've got LB here, which means lateral blast. And basically what we think happened was that 9 hours of activity removed enough dome material from an area of the dome, towards long ground, that it generated a blast that was directional towards long ground only. And that event impacted long ground. There are photos of some really large boulders which were deposited in long ground, and houses were destroyed. And this lateral blast rhetoric would appear in the eruption again. Right. One of the things I want to highlight is the text I've got in red are quite significant because it highlights how the eruption would have evolved during the first episode. So initially the first flows were towards the east, and that's simply because we had a horseshoe-shaped crater, in English is crater, that was open to the east. So if your dome is small and confined, then any collapse would actually be funneled towards the east, as the first dome collapses were. However, in May 97, we started getting rock falls in other directions towards Truitt and down Mosquito Gut. And the idea is that the dome was beginning to get big enough that it can put flows over the edge of the crater in directions which are not constrained by that horseshoe-shaped gap. So in August, we had Plymouth being destroyed. In August 97, we had a number of volcanic explosions in August as well. Very systematic explosions, which were happening roughly like 12 hours apart. And those were quite amazing to see. There was another series of volcanic explosions in September and October of 97. But I think one of the highlights of phase one was the Boxing Day event, which more or less removed the village of St. Patrick's from the map. And that again was a lateral blast that was generated from the collapse of the Galloway's wall, which exposed a gas-rich portion of the dome. And you had a directed blast towards the west, which removed St. Patrick's from the map. And people who would have seen photos after that blast would definitely grow to appreciate the power of a lateral blast, because it more or less removed the soil. So there was no soil left. All that was left was just bare rock.